This is a tutorial to understand Euler's integration method for continuous time simulation. And in this case, we're going to be looking at a problem that we've seen starting at the beginning of class, looking at the dice fighters model. But in this case, we're going to be looking at it from the lens of Lanchester's square law. So in this problem, we understand that there's two fighting forces. A, which is the size of the red team, and B, which was the blue team size. Now in this problem, we're going to be treating these two as continuous variables rather than looking at them as discrete variables as we did previously. So in this case, the problem is set up such that the red team has a strength, alpha. So alpha is the hit chance for the red team. And similarly, beta is the hit chance for the blue team. And in our examples in class, we had said that alpha was 1 out of 6. So being able to roll a 6 was considered a hit for the red team. And for beta, we considered that to be 3 out of 6, being able to roll a 4, 5, or 6 to consider a hit. And in our in-class example, we had considered the initial state A of 0 to be 20, and the initial state for B to be 10. Now, to represent this as a continuous time model, we have to express a relationship for the differential equation. And in this case, we had said previously that the time change rate for the red team size is proportional to negative beta times b of t. So in this case, what this means is that the red team is losing, right? So that's why there's this negative sign. They're losing a size, and it's proportional to the blue team strength beta and the current number of blue team forces b of t. And similarly, there's another equation to express the time rate of change for the blue team, dB dt, is very similar, negative alpha times a of t. So similarly, the blue team is losing forces, and it's proportional to alpha and a of t. So if we use these differential equations, using Euler's integration method, we can define state transition functions for these two state variables. So remember that the state transition function, I've been using the symbol delta, and for a particular state variable A, it's a function of the state variable itself, its derivative, and the time step. And the notation that we've been using in this class is that it's always equal to the current value of the state variable plus delta t times its current derivative. So if we substitute in the knowledge that we have for the derivative, we can rewrite this equation that the state transition function for the red team is the current force size A of t plus delta t times negative beta times b of t. And similarly, there's a state transition function for the blue team. which is the current blue team size, B of t, plus delta t times dB dt at that particular time, which, rewriting using our knowledge of the differential equation, is B of t plus delta t times negative alpha times A of t. So using these two state transition functions, we can start to evaluate a simulation. We can start manually, for example. So if we know that A of 0 is 20, so there's 20 red team members at the initial time, and B of 0 is 10, we can then use those to compute the values at the next time step. So let's say we're using a delta t of 1.0. So alpha, or A of 1.0 is A of 0 plus 1.0 times negative beta B of 0, which is 20 plus 1.0 times negative, so beta was 3/6, times 10, so B of 0 is 10. So this, if we just do this math real quick, 20 plus 1 times negative 5, so we're losing 5 units from the A team size, so we end up with 15. And similarly for B of 1.0, it's B of 0 plus 1.0 times negative alpha times A of 0, which is 10 plus 1.0 times negative 1/6 times 20, which is 20 divided by 6 is just over 3. So 3 and 3 1/3. So they have just under 6. So let's say 6.67. So this helps calculate the first couple of time steps, and we could continue this saying, A of 2 is A of 1.0 plus 1.0 times negative beta times B of 1.0. So using these updated values, we can then compute the next time step. So just in this example, for example, it's 15 plus 1.0 times negative 3/6 times 6.67. However, if we really want to do this for a longer period of time, we want to automate this. So that will be the second part of this tutorial using Python. So I'm going to switch over to my Python script. And here I'm going to write a simulation that will use Euler's method using the state transition functions that we've identified. In this example, I'm first going to import NumPy as usual. And I'm also going to import matplotlib.pyplot to do some plotting later on. So to perform a continuous time simulation using Euler's method, I'm going to first set up a couple of parameters. I'm going to say the initial time is starting at 0.0, and the final time, let's say that we want to go up to 10 units of time. And let's say we want to take a delta t of 1.0, so a time step of 1 time period. Now to help store some of the data, I'm first going to compute the number of time steps that this simulation will require. So the number of steps is the final time minus the initial time divided by the time step. And I'm just going to cast this as an integer, so round off any additional value. So just going to run this and take a look. for this case, it is correctly saying that we'll need 10 time steps to go from 0 to 10 with a time step of 1.0. So now that we have a number of time steps, we can create some arrays to store the outputs from our simulation. So I'm going to create an array T, start with zeros for the number of time steps that we'll have. This is going to score the time at each time step. This will be very helpful if we use delta t's of less than 1 to be able to easily plot the data. I'm also going to create an array A, fill it with zeros in the number of time steps. This is going to store the red team size, and also an array B to store the blue team size. So now that I have these three defined, I can start performing the simulation or start setting up the simulation. We know that the initial conditions, so the first value of the red team size at time step 0, or in the first time period, is 20. We also know that the initial blue team size is 10. And the initial time is given in the t initial variable. We also know that alpha is 1/6. So keeping in mind to use the decimal point to make sure that it doesn't do integer round off. This is the red team hit chance. Beta is 3/6, which is the blue team hit chance. All right, so I think these are all of the parameters that we need for this problem. We can then perform the simulation. So we want to iterate over all of the number of time steps, and I'll store that current time step that it's evaluating as this temporary variable I. So I takes on values 0, 1, 2, 3, and in this case, all the way up to 9. In this case, however, we're going to be computing and storing the value at the next time step. So for example, the red team size at the time +1. And since we've only allocated space to store the number of time steps, and we're storing the next one, essentially in this case, we need to only iterate over the number of time steps -1 so that we don't overflow this array storage. So now we can simply apply Euler's integration method. We know that the state variable at the next time step is equal to the value at the current time step I, and then add delta t times the differential equation. And as we were looking before, the differential equation for A is negative beta times the number of the blue team size, which is simply B of I. So we can do the same, we can express the same type of equation for the blue team. Its value at I+1 is its current value, B of I, plus delta t times negative alpha times a sub I. And just for completeness, I'll also store the updated time. The time at in index I+1 is the current time t at index I plus delta t. So if I run the simulation as it is, I see that there's not any errors. I can take a peek at the A and B matrices, or the A and B arrays, and it looks like we're getting data. So let's plot these real quick so we can get some visual reference. So I'm going to create a new figure using pyplot, and I'm going to plot these as a step function just so we can see some of the artifacts of this Euler's integration method. I want to plot on the x-axis the time t, and the y-axis will be the size of the red team force A. I'm going to use a red line to plot this, so using the plot option -R. I want to use the where equals post option to adjust the step function properly to make it on the right-hand side of discontinuities. And I'm also going to label this as the red team, or A. So I'll do the same thing to plot the blue team. I'm just going to copy and paste that line, change it to use a blue pen, and change it to the blue team label. And let's change the Y label to team size and the X label to time. And I'll add in a legend at the best location. All right. So here's our plot. It looks reasonably good. We can see that the red team force drops or falls from 20 down to some level, and then it appears to rise back up. The blue team is just constantly falling. We do see, however, that there is a small issue where the blue team is actually going negative, which doesn't make intuitive sense. So this is actually a function of our differential equation. There's in the basic format, there's no extra rule or logic to restrict the team size from going below 0. So we'll fix that in just a moment. First thing I want to do though is to make this look a little bit more, I guess, less discrete. So add in some more time steps. The way that we've written this so far is that it's actually really easy to change our time step, our delta t. Just need to change it in this one location to maybe make it 0.01. It'll automatically recompute the new number of time steps, adjust the array sizes appropriately, and compute the updated values using the same Euler's integration method. So with this much smaller time step, we get a much more continuous plot. It's looking more like a continuous time simulation, which is good. The next thing we may be interested in is to fix this problem of the blue team going negative. Here, what we really have to do is just adjust the differential equation that's being used to compute the state updates. One other way of doing this in Python, rather than writing the differential equation explicitly in the formula, is to define a function. So, for example, I can define a new function dA dt. So this will be the derivative of the red team size. How does the red team size change? This will have a couple of parameters. The first parameter that we need is the blue team size b. We know that the red team size is a function. The differential equation for the red team size is a function of the blue team size. It's also a function of beta, but we can kind of include that as one of the model parameters. So the first step is just to replace what we currently have. So right now we have the differential equation for A is negative beta times b of I. And if we pass in b as an argument, we don't need to necessarily index it in this case. So we can return negative beta times b. And here in the integration time step, we can then call this function dA dt and pass in the value of the current blue team size b of I. Now in this function, this is just a temporary variable. We could call this really whatever we want. We could call it blue, and we'll get the same type of results. And just to prove that to you, we can run the simulation again, and we get the same outputs that we did before. We're just calling this function dA dt and passing in the value of the current blue team size, which is using this temporary variable to compute the derivative. We could do the same thing for the other differential equation, dB dt. Maybe I'll pass in the temporary variable red. We know that it's negative alpha times the red team size. And now we can replace our differential equation with dB dt, passing in the current value of the red team size as the argument to compute how the blue team changes. All right, so we're getting the same results. That's good. The only difference now that we have to do is adjust our differential equations to kind of stop changing the values after one of the teams has reached 0 forces. So to do that, we're actually going to need to add in a second condition for both of these. It needs to know both the red team size and the blue team size to compute the differential equation in both cases. So I'm going to add in these two arguments, red and blue, to compute the change in the red team size, red and blue to compute the change in the blue team size, and correspondingly I'll add in that extra argument where I'm calling the function to provide both the red team force size and the blue team force size at each time step. So now computing these state updates, we can run it again, make sure we still haven't fundamentally changed the outputs. What we want to do is to return this only if either the red team size has some positive number of forces left, and the blue team has some forces left. Otherwise, we want to just essentially end the simulation and no longer change the force size. So this conditional statement I'll add to both of these. Again, the way to read this is that return the normal differential equation value if the red team has more than 0 fighters and the blue team has more than 0 fighters. Otherwise, return 0 for the derivative, meaning that we don't want to change the value anymore. So if we run the simulation, we can see that now, right at this very point in time when the blue team has 0 forces remaining, the size of the blue team no longer changes and it remains constant, and similarly for the red team. And the way to interpret the results from this plot is that essentially the red team has won. They have more than 0 forces when the blue team